Thank you, Ken, for introduction. This is a part of my work as a PhD candidate at Polytechnique Montreal. And actually, the motivation for this work was some comments I've got from one paper we had at FPGA last year. And I'm going through this methodology in here. I'm going to talk about it. And I try to present our ideas in a consistent way. I'm not going through all details in code snippets because they are tedious, so I'm trying to get more illustrative examples there. You're supposed to have a timer in here, but it's not going down. Yeah, so the outline for this presentation, we're going to start with a intro and motivation, and then you present our methodology, and then we're going to go through a real-life example for our methodology, and then you present some results and conclude this work and this talk. So it's clear in here in this conference, you're talking about FPGAs and high-level synthesis a couple of times in this conference. It's clear for everyone that HLS open doors for everyone and who wants to start working on FPGAs, and then there's no object on it. And this is just because C++ and C coding is easier than RTL. Yeah, it is. I'm not talking about mode threading stuff and mode processing stuff, but regular C programming is normally easier than RTL development. And current state-of-the-art HLS tools deliver good results, and they are fast in prototyping, and the co-simulation and simulation are fast compared to RTL simulation. This is true as well. So the question that arises, is there any problem? And in our standpoint, yes, there is. Actually, there are. And normally to achieve good results with HLS, you have to go through some microarchitecture details, even if you're writing C or C++ code. And those microarchitecture details writing in C++, they, in our point of view, they compromise software quality. You know, trading off with hardware QR, and then if you want to go to have better performance, normally your software is poor compared to what you could do. And you have to express your operations in a low level, and still, even though state-of-the-art HLS tools, they claim to support modern C++, they're not quite ready yet. And in the last talk, you're talking about design patterns, but there are not so many outside there. So it's still missing some design patterns for HLS design, for more complex and reusable code and more modular code. And in our standpoint, the design methodology for HLS it follows a unidimensional view when you're trading off hardware quality with software quality. If you want to improve your quality, normally you're going in your software quality, your hardware QR normally goes down. And it's kind of true. And in our standpoint, those two metrics should be independent. And this is what you're targeting this talk in here. You're targeting to improve performance and still having reusable code and modular code and more comprehensible code as well. And how do you do that? And you put those axles completely independent, and you try to improve and to use more recent and more modern constructs in C++, trying to explore STL-like design pattern. And then you finally introduce your methodology in here that's called module per object. And module per object actually is a kind of design pattern which each object in your C++ code, it represents a functional hardware module that is aimed to improve performance or to keep performance, improve code readability, and code portability as well. And for that, you're trying to extensively use templates on it. I know some of you may agree that templates difficult code readability, but they fairly improve code modularity. And we show as well in this work how can you use modern C++ constructs to design to derive a hardware implementation from a high level or a DSL language. And we demonstrate that using 3 design examples: a packet parser, a flow-based traffic manager, and a digital web converter. So in our work, you have five premises that you try to keep in order to deliver those claims I just mentioned. So templates. You exploit templates in order to fine-tune parameterize our objects and to provide as well the configurability you need to reuse the code. And you systematically use const and const expression variables and functions to parameterize those objects. And as as we can, you try to use standard C++ constructs and some types and some functions that are available in STL in order to reuse code that has been written, and inheritance and polymorphism as well. And finally, you're exploiting a smart constructor to initialize some class members and to reuse some code. As an illustrative example in here, you're going to demonstrate how can you translate some kind of high-level domain-specific language, sorry, to describe a packet parser. This language that I'm showing there, this is P4. My friend in here just talked about P4, and this is an implementation of a parser state machine. They're parsing actually 5 protocols in a layer 3 device, and that description there generates a DAG graph that is there's presented there that could in turn generate that kind of hardware architecture where each box in there represents a protocol and you have some kind of pipeline registers, and then you follow a very, very straightforward pipeline architecture. And then how can you exploit templates to parameterize the nodes in that graph? So if you're looking at that graph, you can imagine that a parser, you need very few information about each protocol you're talking about. You need to know which the next transition have to go, and the number of bits you need to extract, and as well the header size. So as template parameters, you're passing through each graph, each node in that graph, you're passing some physical characteristics that are bus size and the maximum packet size that are supporting in our architecture, and some node characteristics that are passing. The header size, it means the number of bytes that each header has, and the number of possible next header to go, because it's a state machine, you have to know where to go and the number of transitions you have. And for each of those nodes in that classes and objects in that graph there, you're implementing a static polymorphism to avoid re-implementing, rewriting code. And finally, you have a kind of header template that is basically that gives us the information about each node. That is an array of tuples that gives the position, the key position that you have to look at the header to find the next transition, the value that you have to look at, and the next header, and finally the number of headers to extract. The second premise that you have is exploiting const expressions. So since you're talking about templates, all the times for parameterizing templates in C++ needs to be known at compile time. And then for that, in that sense, const expressions could be a very handy tool for that. And one example in here, I'm showing you how can you get the number of bits to represent an integer or an arbitrary sized integer that is totally computed at compile time. And then if it's known at compile time, you can fine-tune your objects or classes using the result of that expression. next premise that you have in here is you have to go through modern C++ and exploring STL constructs. In this project in here, in this paper in here, you have used all of those constructs that are available in the standard template library that are there. So you have used the pair, you have used array, tuple, and some algorithms that have not introduced any overhead at all in the generated hardware, and some kind of type traits that are nice for compile time and for choosing which kind of piece of code you want to compile, and for sure iterators and ranged beta 4 are very handy as well for code readability. Since you do not have anymore to specify loop bounds and you go through your loop without specifying the iteration, and arithmetic type deduction through auto keyword and the decal type. They are pretty handy as well. So in the parser, they are pretty much homogeneous in terms of processing, but each of the components, each of the node has specifics. And then for resolving these specifics, you have implemented some derived classes in here. There you have some base classes in order to extract specifics for each header. For instance, if you're talking about IPv4 and IPv6, they have a specific difference between them. Is that this header size for IPv4 is variable, while the header size for IPv6 is constant. And then for implementing so, you have defined just once header format class there that has two derived classes in here. One for the fixed header format, and the other one are for the derived header format that you can call using the same call as showed there. If you got header size by overloading, I'm going to take this one or that one, depending on which object I'm instantiating into my code. And the goal in here is to reduce or eliminate code duplication. And as I said, we are using CRTP for that. And the fifth premise in our work is to use the smart constructs to initialize class members. So you can, in constructs, you can call some different methods as functor and lambdas to initialize special elements or special class members, and then you can as well improve performance or reduce area footprint since you can now resolve stuff and the compiler disable to initialize class members using constant values instead of runtime values. So, as I showed in the beginning, this is the final goal, the final architecture you're targeting here. Is a pipelined implementation of a packet parser. So, to implement that, we started a description in P4, and then you generate class templates for that, and specialize each of the class templates with specific parameters that have extracted from the P4 program. And those parameters are then header definitions that are translated to class templates directly. And then the pipelining here is inferred by using static objects for each object in C++. And then those pipeline registers there are correctly inferred. And the multiplexers in here are just inferred using the ternary C operator. I know that multiplexers in FPGAs, they are costly, but you have to use them if you want to go through a data flow processing model. But it's still facing some problems using even modern HLS2 we're still having some problems. It means that HLS tools are not quite ready. There's still lag for modern C++. I know that the question has just arrived there. So polymorphism is not quite well supported. Even though you try to use CRTP, you struggle with it. If you have to access class members in the derived class, you're not able to date. At least using my examples, I was not able to. This is one limitation that you found. And if you're going to parameterizable design using lots of templates, it took longer times to compile comparing to pure C or C++ descriptions. And there's still a lack of support for modern C++. So I'm going to show you some results that I got through here. Here's the test bed I have used, and then I have used Vivado 2015. I know it's pretty old, but it's the version that I got the better results. And the device you're using is a Vertex 7, and you have used CC Finder X to detect code clones, and you have three test cases: a packet parser, a traffic manager, and a digital up converter. In the first example in here, you're comparing to state-of-the-art. This is work for Benachek from the FCCM 2016. That is a packet part that is able to process 100 gig per second. And then, as you can see here, using our methodology, you're able to comparing to the golden model that is written in VHDL. You're comparable in terms of latency in here, but you're losing in terms of LUTs. When you're comparing to a generated RTL from P4, you're able to beat them in terms of latency, and you're also decreasing the number of LUTs in here. For the second example you have, it's a traffic manager, and then you're comparing against the original implementation that is, unfortunately, is not open source in this code, but you have instrumented that code using our methodology, and as you can see, you're able to beat them in almost all the metrics there by factor of 10% at least, but you're increasing the number of lines of code. This is explained because you have put some library that can be reused afterwards in another and different examples, and you have removed it from the original code and put aside, and that's the reason that the lines of code have increased. And finally, you're comparing against an application node from Xilinx that implements a digital up converter. And in that case, you're able to beat the application node in all the aspects, as you can see in here, by at least 10% in terms of frequency, and almost the same thing for the LUTs. And in that case, you have less lines of codes, and you have no clones code, no instance of clones detected in your code. It means that in the original code, you have replicated code inside, and in your version, you have eliminated them. Finally, just to summarize the presentation, yes, HLS is good, but it's still, you still have some limitations in terms of design methodology. And in this work, you have presented the MPO methodology. That's an STL-like design methodology for HLS design that's designed for improved performance, to improve code modularity, and to improve code readability. And now I'll be happy to take questions. Thanks.
A quick question. I'm Ben Schaefer, UT Dallas. When you say HLS, it's not actually HLS. It's Vivado HLS. It's the tool that has the limitation when you see the C++ support and so on. Did you try Catapult, Stratos, some other high-level synthesis tools?
I have tried LigUp. But LigUp does not have
a good commercial tools.
Yeah, I mean,
commercial tools.
Yeah, I haven't tried another one. The only one I have tried was Intel HLS compiler, but the code just did not compile. And Catapult you haven't tried.
Right.
Or from Synapse or.
So would you change your conclusions based on this, saying that Vivado HLS cannot deal with, has its limitations?
Yes, you may. You may change.
Okay, all right.
Thanks. I just wanted to comment that we are working on C++11 and C++.
I can hear that.
Sorry. Is that better? Can you hear me?
Yeah, yes, I can.
We are working on C++11 and C++14 support, so I can't say when it will come out in the product, but definitely for doing abstractions like this, it's really critical to have autotypes and decal and access to a lot of metaprogramming libraries and things like that. So, cool, thanks.
Thank you.
Any other questions? All right, I have a question. Could you go back to your evaluation slide?
Of course.
Sort of, it seems as though you have succeeded in your goal of sort of.
In which one?
This one's fine.
Okay.
It seems as though you've succeeded in your goal of sort of having your cake and eating it too. But could you give us some intuition of where the gains are from?
Yes, I could. Actually, I could. Since you're getting back there, in here, since you're getting back in here, each of those elements on that node, they are fine-tuned for each specific application, you know. Since you're using templates to implement so, you can have very, very accurate bit level in terms of bit level operations that could lead to better performance and reduce the error in comparison to other works, actually. And this is the main reason that you have extensively exploited templates in that work, in this work specifically.
Chris Neely, Xilinx. In terms of like writing parsers or designing parsers, they're usually really difficult when you have a lot of like optional headers, like VLAN, for example.
Yeah.
I was wondering why you don't have that in your example.
Actually, in that one, I don't have, because, you know, if you go through the reference number 4, you're going to have an example there. I just got one simple example to show in here, but yes, indeed, you have header extensions that, for instance, VLAN goes right here, and between Ethernet and IPv4, or you could imagine as well, MPLS goes there. And then, in that case, you're going to have a different parser graph, actually. And this was just an example for, you know, for a quick presentation to go through easily than a more complex example. But if you want some more details, you can talk offline. It's not a problem at all.
All right, let's thank our speaker.
Thank you.